Hooray, we're nearly finished with this second unit on aqueous reactions. This lesson is on redox reactions. Again, this is mostly a review from Regents concepts. You have to have a very firm grasp on your oxidation states and identifying redox reactions. So you'll be able to recognize redox reactions, account for oxidation states, and with examples in class, you'll be able to do stoichiometry calculations with them, of course. So this do now question, what's the net ionic equation for a neutralization reaction? So neutralization reactions occur when you have an acid plus base forming a salt plus water. So the goal is the formation of the water, which is a molecular substance, so that would be present in your net ionic equation. How do you get water out of an acid and a base? You have the acidic part of the acid, which is hydrogen, and the basic part of the base, which is hydroxide. Hopefully you remember this sort of acronym or whatever mnemonic device. Leo says GER when we talk about redox reactions. These processes are coupled. You cannot have one without the other. A redox reaction occurs when electrons are transferred from one substance to another. If the reaction is spontaneous, energy can be transferred. This is something that you would find in a voltaic cell. We will do a unit on electrochemistry later in the course. You can also have heat, changes in heat as well. If you have a non-spontaneous redox reaction and you force it to occur with the assistance of electricity, that's when you have something like electrolysis, and we'll talk about that as well. A redox reaction must have a source of electrons and a sink. So the source is where you get them from, the sink is where they're going. Remember that oxidation is the loss of electrons. The substance that gets oxidized is also known as the reducing agent. That term is excluded from the curriculum, but if you take biology in college or you take AP Bio, you're going to see these terms oxidizing agent and reducing agent, so you definitely want to understand what those mean. You do need to have a grasp that oxidation is the loss and reduction is the gain. That's where you get that Leo says GER. A lot of reactions can be classified as redox that you could also classify as something else. So, for example, combustion reactions are redox reactions because there's a change in oxidation states for some of the elements. Single replacement reactions are redox reactions. Synthesis, decomposition are usually redox. Double replacement reactions, which also include neutralization reactions, are not. So like your precipitation reactions that we've looked over, which are double replacement, are not redox reactions, but a lot of other things can be classified as that way. So could be classified as a synthesis reaction, but also as a redox reaction because you can change the oxidation states. Any element that is uncombined will have an oxidation state of 0, and then when it's in a compound, the sum of the oxidation states in the compound have to add up to 0. So because there was a change in oxidation numbers, that can be classified as a redox reaction. You need to know how to assign the oxidation states to elements. We went over a bunch of rules in Regents chemistry. You can kind of summarize them with this little mnemonic device, FIMHO. You really don't have to memorize these rules per se, just know how to use them when they come up. So the F stands for free elements in fluorine. If you have a free element, the oxidation state is going to be 0. So any element that's uncombined. If you have sodium, if you have chlorine, if you have iodine by itself, if you have oxygen by itself, if you have 8 units of sulfur in a molecule, all of those things would have oxidation states of 0. Fluorine will always be a -1 when it's in a compound. No exceptions. Fluorine's always a -1 oxidation state. The I is for ions. If you have an ion listed, the oxidation state of the ion is the charge that's listed next to it. So even though it's like, oh, but it's by itself, if there's a charge listed there, that is the oxidation state. The M is for metals. You need to know that group 1 metals are +1, group 2 metals are +2 oxidation states. Any other metal, like a transition metal, or something like aluminum, if you're not sure, use the other element that it's combined with to figure out the oxidation state that it has. So for example, zinc chloride. Well, chlorine's a halogen. Halogens in compounds if it's a binary compound, they're a -1. So the zinc would be a +2 to cancel it out. And then for the 2 iron and oxide compounds, oxygens are going to be -2 in almost every case. So this iron's a +2. This iron would be a +3 to cancel out the quantities and charges. H is for hydrogen. Hydrogen will always be a +1 except if it follows a group 1 metal. Because there's a rule for group 1 metals have to be a +1. The hydrogen has to cancel out that +1, so hydrogen would be a -1. In all other cases, hydrogen is a +1 oxidation state. So ammonia usually trips people up because they're like, oh, but the hydrogen is listed second. It doesn't matter. Hydrogen is a +1. Each hydrogen is a +1, so the nitrogen's a -3. For O is for oxygen. Oxygen is going to be a -2 in cases of peroxides or if it's bonded to fluorine. So in a peroxide, again, because we have this rule for a group 1 element, each sodium is a +1 oxidation state, then each oxygen has to be a -1 to cancel out mathematically, or if it's bonded to fluorine. So this compound, again, doesn't show up often, but we have a rule for fluorine. Fluorine has to be a -1. There's 2 of them, so the oxygen has to be a +2. Remember that the oxidation numbers have to add up to the total charge on the compound or the ion. So if you had a polyatomic ion like nitrate, and you had to come up with the oxidation states of these elements, each oxygen is a -2 oxidation state, times 3 is -6. Now to figure out the nitrogen's oxidation state, you have to look at this overall charge on the polyatomic ion. The overall charge on the entire nitrate has to add up to -1, which means this nitrogen has to be a +5. For trends for redox, if you have an active metal, metals tend to be losers. Losers are easily oxidized. For non-metals, they tend to be gainers, and they're easily reduced. You don't have to memorize any sort of activity series. We'll talk about that, these processes later. So here's just a couple examples of finding oxidation states. I'm not going to go through all of these. So this first one, this is potassium dichromate, figuring out the oxidation states for each of the elements. Potassium is a group 1 ion, so it's going to be a +1 for each of those. So that's a total of +2. Chromium's a transition metal with a lot of oxidation states, so don't do that next. Do oxygen. Oxygen would be a -2 times 7 is -14. So the chromium has to add up to +12 so that the 2, the 12, and the -14 all add up to 0 for that compound. Because there's 2 chromiums in the compound, each chromium would be a +6 oxidation state. This next one, the carbonate ion, I'm going to rewrite this over here so I have more space. The carbonate ion has a -2 charge overall. Each oxygen has a -2 charge itself, so that's -6. So that carbon has to be a +4 oxidation state. So when it adds up, it totals up the +4 and the -6 add up to -2. Let's look at this phosphorus pentachloride. The chlorines would each be a -1 times 5 is -5. The one phosphorus has to be a +5. This sulfur tetrafluoride, each fluorine has a rule, -1 times 4 is -4, so the sulfur is +4. Which of the following are redox reactions? Identify the substance being oxidized or reduced. So you have to look at the oxidation states. If you find something where the oxidation numbers are changing, then you have a redox reaction. So for A, zinc starts out as a 0 because it's a free element. Hydrogen on the product side is a 0 because that's a free element. Now, when you look at the other substances, when you have hydrogen in a compound, its oxidation state is not 0 anymore. When you have zinc in a compound, its oxidation state is not 0 anymore. Does it matter what the oxidation state is? No. All you know is that it's changing in some way. So this is a redox reaction. If you look at B, this one's more complicated because you don't have any free elements that you could just lean on. So we'll figure this one out. So this would be a +6, +1 minus 2. This is a -2 +6. And this is a +1 minus 2. So if you look at these oxidation states, chromium is a +6 across the board. Each oxygen is a -2 across the board, and each hydrogen is a +1 across the board. So this is not a redox reaction because there's no change in oxidation state. And for C, copper is a transition metal with multiple oxidation states, but chlorine, we can rely on that. That's a -1, so the copper is a +1. And then look over here. We have copper by itself, so it's a 0 over here. So there's a change. So who cares what the rest of it that's going on? Well, I guess we have to, because you have to identify what's being oxidized or reduced. I should read. So we can look at these other substances here. So in this compound, we have a -1 for the chlorine and a +2 for the copper. So look, we have copper going from a 1 to a 2. Chlorine's not doing anything. And then we also have this copper going from a 1 to a 0. So this is copper getting oxidized, and then the bottom arrow is copper getting reduced. In A, we have zinc getting oxidized because it's changing to a positive oxidation state, and hydrogen starting as a positive oxidation, +1, and ending as a 0. When you have to balance redox reactions, you want to try to balance the loss and gain of electrons. We're gonna do examples of this in class a little bit, so I'm just gonna leave this here. It's not difficult to do, but you have to have a grasp on oxidation numbers. If you can't do oxidation numbers, you're honestly you just have to do it. Just do it. Nike. I'm not sponsored. Subscribe below. Bye.